fatal day, and the wind begins to speak with a roar that no man can fail to hear. In a 40-mile-an-hour gale, the center span weaves like a ribbon in a swinging twist that you wouldn't believe possible unless you could see it as you do now. There's an automobile caught on the heaving roadway. The 11,000-ton center span twists.
Of course, you've all seen this probably in your high school physics classes. Galloping Gertie, this 1950s movie of the Tacoma Narrows bridge with a wind blowing at constant velocity over the top of it, an external flow, if you like, and related to the things that we've been talking about in this class. We've talked about how Reynolds number changes the flow field, and at intermediate Reynolds numbers between the laminar regime at low Reynolds numbers of 1s and 10s to turbulent ones at 1000s and 10,000s, there's this intermediate range with this shedding of vortices from top and bottom around a sphere or a cylinder, and this is a manifestation of the same thing. The vortices are shed at some frequency. If the frequency that they're shed in happens to match the frequency of the structure that they're coming off, such as the deck of this bridge, then it gives a boom, 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 just like a guitar string. It's exciting at the same natural frequency of the bridge, just like a guitar string has a natural frequency. And it builds the twist in this particular case until ultimately it falls apart. And so now everyone's wiser that you have to take into account what the natural frequencies of things are, and you could either change what would happen in terms of the natural frequency of the bridge, or you change the shedding of the vortices on the side, but that's a consequence of that. So that's one form of external flow. What else do we have that I get for you?
Final preparations are underway for the single most dangerous test in the entire program, the Flutter Test. During the flutter or flight vibration test.
So I just pulled some things together. This is a flight testing of the A380, the double-decker Airbus plane that's the competitor to the 747, the jumbo jet, which I hear the last United jumbo jet, which was actually a picture. The movie we looked at of a wing 2 days ago was out of Chicago on a United 747 sitting on the upper deck. And so the last one apparently is coming out of service this week for United anyway, and Delta are about to follow. So this is the A380, must have been around for a few years now. And this is about flight testing of it under specific conditions, and actually conditions that get taken up to quite high velocities, high Mach numbers. And so we know that as velocities increase, the stresses on a plane would increase also. We know that the forces on a plane would increase in the turbulent regime proportionally to velocity squared. So you double the velocity, you quadruple the forces that are applied on the system. And so this is actually flight testing in taking it towards the speed of sound, Mach 1. So if I gave you the sound on this and shut up.
Somewhere over the Atlantic Ocean, the A380 inches its way towards its target speed. Mach 0.92, Mach 0.93. But suddenly they hear a noise. Chief Test Pilot Jacques Rosé has felt a twitch.
Can you hear that?
After a quick consultation between the air and the ground, the flight crew decide to immediately halt the test.
Amazing plane.
As soon as the A380 touches down, the crew hurry into the aircraft, where they quickly find the source of the problem. Because of the extreme vibrations, a large section of the undercarriage has become detached. Aircraft 1 will have to go to the hangar again, causing yet another delay that Airbus could definitely do without.
Okay, so problems as you get closer to Mach 1. They were up 93% of Mach 1, I guess. So 93% of the speed of sound. And we'll talk a little bit about compressible flows today. So you see vortices coming off the wings. We've looked at wings in plane section, always looking at the fact that you can take a section across cut through the wing, and we have a plane section we can look at. But obviously there are flows of swirling vortices along the wings. Sometimes on planes' wings you see, I'm going to just stall that, you see these winglets on the end to stop these vortices rolling off and losing power of the wing in that particular one. Where else is this? I'm losing this. What is this? Don't want that. Don't really want that. Don't want that. Don't want that. Nor that. Oh. So this is relatively short also. I guess they don't all go to zero if you put this is Felix Baumgartner. This was the inspiration of one of the finals, actually. There's a question, I think, on one of the finals of what's the terminal velocity of a guy who jumps out at 128,000 feet above the Earth's surface, where we know that the density of air is slightly less than it is at ground level. And so we know that in coefficient of drag and coefficient of lift, it's an Euler number. Pressure divided by rho v squared, velocity squared controls it, but also the density of the air, which you can either think of yourself dropping through static air or moving air moving past a static target. And this, I guess you've got to have guts to do this. I'll see if Red Bull actually file a copyright claim on this after the fact. We'll let it go to the end. Sorry.
A stable descent. And Felix is back to red safely. Record holder.
So the questions are, how quickly is this guy moving, and how do you calculate exactly what that is? And that's kind of something hopefully we'll get to do today. And I thought this was kind of fun as well. I just saw this on the news the other day. Isn't that cool? It's funny to watch about the second part of this. Let's go through to the end of it. Yeah, it's amazing. Looks like some of the old gravel pits that are close to Heathrow Airport in the west side of London. I think that wasn't planned. But
every time you take this equipment out, you never really know how it's going to work out. It's all very new. There's no rule book for this. There's no guidebook or manual. We took a little bit of a swim on run 4, but that just proves we're trying to push boundaries.
Yeah, good attitude, yeah, don't you think? Trying to push boundaries. Well, yes, that's great. All right, so that's it. So that's kind of why we might be interested in some of these things beyond the activities that we're looking at. I guess there were a couple of others as well. Let's just go through them all. And this, I'll cut we don't need the music. So we'll also, in the same way that you can think about Felix Baumgartner dropping through the air at whatever velocity he goes at, you could calculate it should be something like 200 miles an hour, terminal velocity. You can also figure out what the terminal velocity might be for grains of soil as they go through water, as they settle out in rivers, as making oil reservoirs of the future, for instance, but also for measuring grain size distributions in fine-grained soils. One way to do that is to measure how long it takes for stuff to settle, and that's a measure of the diameters of the particles. And so they clearly, not clearly, but those two are in different regimes. We talked at low velocity regimes where viscous forces dominate in drag, high velocity regimes where, shouldn't this be zero? High velocity regimes where pressure forces dominate due to stagnation. And this is the case for the low velocity regime where viscous drag around the particles controls how they settle. And if you look at the stratification, in the biggest particles are at the bottom because they settle fastest, and the finest ones are higher up. So they're an indication that there is a difference in settling velocity in the record, as you see. And I'm trying to think what this one. Yeah, this is really cool too. So, welcome. These are models of an ink drop in a liquid, so an ink drop in water. And actually these are numerical models, just like the ones we were using, I think, on Wednesday to look at flow around an airfoil. Same kind of idea. You divide the whole system up into lots of these little cells, and you allow the fluids to pass through them, and you look at the resulting patterns that form. I think it's kind of interesting. That makes a ring that ultimately you have these globules that come off, and they're denser than the fluid around them, so they keep on sinking, and then they become unstable as they flow a bit more, and they make these rings, as you can imagine having vortices flowing around them that are making them do that. So a model, again, sophisticated model, and the observation to back it up on the side. Really quite beautiful in some respects. And so maybe we don't need to see any more of that. So that's kind of where we want to go today to be able to understand what the final components are that we might want to talk about in this class for this last meeting that we might have today in person. And so this is kind of the agenda. And so, as we've seen, we might be interested in knowing what the forces are that are applied on structures, and we know kind of how to do that, so long as we can always get the magnitude of these coefficients somehow, either by modeling or by looking at tables that are recovered from either models or from experiments, to be able to figure out what the drag and lift coefficients are. We know that the drag coefficients are for forces parallel to the flow, and lift is for forces which are perpendicular to the flow, my little notation for that. And we know, most importantly, our most important figure that we've drawn in this, which I'll redraw because it will start us off in the right direction, is this Moody-like figure of coefficient of drag or coefficient of lift, which of course is an Euler number. We know that these are equivalent to a pressure. So if a force over an area is a pressure, then this is just a half rho u squared. This is pressure, right? Rather than written in this way. And we know that these relationships for Reynolds number, which is a velocity, a density, a characteristic length, and a viscosity. And we know that the behavior that we expect looks something like this in an idealized form. And that we can divide this into these two regions. And these two regions would be laminar, and this is turbulent. Looks like good writing, handwriting, I say today. This, by definition, is something like some constant divided by Reynolds number, as you see, if it's a straight line or close to a straight line. And if we look at what these things look like, we've drawn them already. But if we have, say, flow past a cylinder at these different flow velocities, I'm just going to draw these in here, then they would look something like laminar behavior. It hugs the contour and comes out the other side and is kind of symmetric on both sides. At higher velocities, we get these circulating eddies on the back. This. And at higher velocities, we get these eddies which are shed periodically top and bottom as it goes around. And we'll look at those in more detail. And so this is the Tacoma Narrows bridge that physically, if you take a picture now and look at what this looks like, it looks like this. If you do it 5 seconds later, then maybe the one that's being shed is coming off the bottom, the next one downstream is off the top, etc., because they're moving downstream with the overall flow. This is always the far field flow velocity. So in other words, this is the velocity here as it goes into this, not the local velocities, because that's something that you'd know. If you know the plane's going 500 miles an hour, then if it's static air, then that's the relative velocity of the air. So that's what we need to know. The other point about this is that viscous forces, or viscous drag, in this regime is high, and pressure drag, or lift, is low. Whereas in this regime, it's the opposite. So in this regime, the viscous drag, there's a boundary layer that develops around this, which is very thin, and therefore the viscous drag is small because there's not, you go directly from the velocity of 0 close to this object to the far field velocity away from it. But pressure drag is very high. In other words, it's all due to the fact that if it was me standing in an airstream, it's me hitting my chest and killing the velocity. Yes, sir?
Why are we relating it to the Reynolds number? Because just from the, I guess, the things there's dependent on it,
it's the same as in any similitude problem. So you want to have geometric similitude, same geometry. You want to have kinematic similitude, which is that the flow regime looks the same in the model and the prototype, which is what Reynolds number gives us. Now, if you want to calculate what the forces are, if we have it at the right Reynolds number, we need to use this expression to be able to figure out what this is. So we're just characterizing the flow regime. Once you're in the right flow regime, you can calculate from that appropriate Reynolds number, which would have a given, so in other words, the other important thing to come from this is that the drag coefficient here is proportional to 1 over Reynolds number, and the drag coefficient in this regime is proportional to, it's flat, right? So that's the other important thing. So yeah, that's where we were going with this. Okay. Yeah. So it has to be at the right Reynolds number to be able to guarantee what's going on. So the other part of this, I think, is that if we keep on going down here, then the other component about this would be really for liquids. It's not exclusively liquids. And this would be for gases. Both fluids, but this would be for a grain settling in water, and this would be for Felix Baumgartner hurtling through the atmosphere, and all that's different are the magnitudes of the Reynolds number. And so the question you asked actually is a very good one, because now what we'll do, one of the things, we'd like to know two things. We'd like to know maybe what the forces are that are acting on the structure, and so we can get that immediately if we can know what the drag coefficient is, if we know what the far field velocity is and the fluid properties and the appropriate area. We can calculate the force directly. But the other thing we might want to calculate is terminal velocity of a grain settling in water or Felix coming through the atmosphere, and we can do that using the same technique by just using force balance. And it's analogous, I'd say, to the sprinkler problem. So you have a sprinkler. You can hold the sprinkler so that there's zero velocity of the rotating head, in which case you calculate the torque that's applied, the force. Or you could allow it to spin where there's no torque applied, and you calculate the velocity of the component. So it's analogous here. You either calculate the force that's applied on the airfoil, if the air's going past it, or you calculate dropping through the air, the force is balanced, and therefore you can calculate the velocity at which the person is hurtling through the air to be able to get to it. And there are two regimes which are different where we can do that, and we will do that now. And so this is basically the idea. So if I go down through here and I separate this off to one side, so let's do it for laminar on this side. And so what do we know? So for instance, if a particle is setting, so there are two examples in the notes, and they're both in the book. One is for a grain settling through water, one is for a hailstone being lofted up by the updrafts in a thundercloud, but they both rely on the same geometry. Actually, I'm going to do it above. The geometry is for both, and I'm going to do it here. And that is, you have a particle, and for that particle you do a force balance. You've seen this before. Buoyant force is equal to the unit weight of the fluid, gamma, rho g, times the volume of the particle. And there's also a drag force that's applied. And in this case it'd be this squirrely d, if you can see that. And we know that the drag force, the coefficient of drag, is equal to what? The drag force divided by half rho v squared area, some area. So it's a relevant area. In this case, the relevant area would be the frontal area of this sphere as it drops through the atmosphere, so pi d squared upon 4. And we also know that from this figure here, that the coefficient of drag is equal to a constant divided by Reynolds number. And if we write out the Reynolds number in full, let's call this the constant for laminar drag, which would be, this is something like 24 for a sphere, I think. And Reynolds number is density, velocity, some characteristic length, which we could choose diameter. Oh, that's a bad choice, isn't it? And viscosity, right? So it's Reynolds number, just 1 over. So this is the coefficient of drag. So what we could do is we can substitute this into here, and we can write that in terms of whatever the drag is. So the drag force is going to be equal to the coefficient of drag multiplied by a half rho v squared a, just this term here. And if we substitute this coefficient of drag into here, it's going to be equal to a coefficient, which is 24 for a sphere, a viscosity, rho v d multiplied by a half rho v squared a. And then we can start cancelling out some components. Velocity appears twice. Density appears twice. And so we can have the fact that the drag force is equal to 24, which is this number, a viscosity. I'm not going to clean it up. So we can calculate it. If we know the area, this is going to be pi d squared upon 4. This is diameter. This is the velocity in the far field. This is a viscosity, and this is, if it's a sphere, this is 24. And so now, if we want to write the force balance equation, we have D plus the buoyant force, which may be inconsequential, minus W equals mass times acceleration. If it's terminal velocity, then the acceleration by definition is 0, and this is 0. And we know all the other components. The only unknown in this is velocity. And so we can solve this. I won't do it, but you can see that you can solve it directly for velocity. Okay? And so the important thing that comes out of this is that in this case, the drag force, as we alluded to before, is proportional velocity. We see that from this component here. This is squarely D, and because of these cancel out. And so in this kind of solution sequence, we end up, the fact that the drag force is proportional velocity gives us a terminal velocity which we can calculate, which would be this value here. And if it wasn't at balance, so in other words, if you're starting from 0 velocity as you drop something, the out of balance force you'd have would allow you to calculate what the acceleration would be incrementally. You could step through it, but we won't do that here. Terminal velocity you can get from that. Okay? If we go to the other side of this graph, here, then we have exactly the same calculation as before. It's exactly the same free body diagram that we'd have. It would be exactly the same force calculation. But now what's different is that you see that as you change the Reynolds number, the drag coefficient no longer is a function of Reynolds number. It's constant. So the fact that this is the case here is that we can go in and we can calculate the coefficient of drag is equal to the force divided by a half rho v squared a. Just taking this from up here. And if we rearrange that for the drag force, we know now we don't have to substitute for Reynolds number in this, because we know that this is just a constant, a different constant. Let's call it C turbulent. And it would be this value here, whatever this value would be. This would be CT. And if we do that, then we end up with just rearranging this for CT times a half rho v squared a. And when we do the substitution of this expression here into this, we'll end up with an expression that gives us a balance equation which has that the drag force is proportional to v squared. And so typically all we need to do is we need to take a square root of that velocity to get whatever of the equation to get that. And so it's different. And so the dependencies of the drag force, in one case for laminar flow, these will be controlled by the viscosity. So viscosity exists in this equation, and the drag force is proportional to the velocity. But clearly in this equation, it's not a function of, it's independent of viscosity. So this is independent of viscosity. It's dependent on velocity, and it's also dependent on density, pressure drag. So the density of the fluid that you're stagnating and its velocity squared make that term. And on this side, this is independent of density. Density no longer exists in this equation because we've got rid of it here and here. But it's dependent on, let's make this v squared here, on velocity and viscosity. So that's the two kind of sides, if you like, of this expression. And it fits nicely into this geometry here. Okay? So that's all. So that's the main portions that you need to know about external flows. That there are these two regimes. They're separated by some number, which may be about 100 Reynolds number, depending on what the characteristic lengths are that you're using. And that on the left side of this, on the right side of this, you'd expect to get different dependencies, mainly because in the laminar regime, viscous drag is a big part of the behavior, and pressure drag is not. And in the turbulent high velocity regime, pressure drag is a big component and viscous drag is trivial. So that's it. So there are a couple of examples in the notes, and you can see them from the last video, which this one will supplant, but you can see those effects in the stuff we did online. I won't do them today, but I'll kind of go through some other things. So the key issues are that if you want to know what the drag forces are, you need to know what these coefficient of drag magnitudes are. Coefficients of drags are going to be dependent on the Reynolds number. In the regime where they're laminar, for any object, there'll be a function of the Reynolds number. And you can get magnitudes from these for different shapes, for spheres, for a hemisphere, for a circular plate, but it matters what the orientation of this is. It's interesting to me that if you look at a flat plate versus one that's a cross flow versus parallel to flow, actually the coefficient don't differ very much. Quite surprising. You'd have thought that this would be much lower drag, and I guess it is lower drag, but not significantly so. And if you look at behaviors for different shaped objects, then it matters. They typically relate to a particular Reynolds number. Nu is just the kinematic viscosity, which is what? Dynamic viscosity divided by density. Sometimes it's a more convenient property to use in these. But it matters what the geometries are and what the directions of flow are. And so you can just look up these different tables to be able to do with this. For plates, etc. I think this is the middle one's kind of interesting, right? For a very small sphere, and the coefficient of drag on this is 1.2 versus this much bigger cyclist's helmet with this trailing edge which tapers down, so you have the wake at the bottom which is minimized just at the tip, and the coefficient of drag of this thing is 0.12. And so in other words, on this figure that we look at here, it would mean a line that was here, which is 0.12, versus one that's an order of magnitude higher than that for the smaller sphere. So in our particular case, this would be the tiny little sphere here, and this would be the huge cyclist's head with the tail on the back that allows the flow to go around it and back. And so I suppose they would be roughly equivalent in terms of the drag forces, because because the cross-sectional area in this, if it's 10 times smaller, then this would be 100 times the area, right, in this particular case. But anyway, so you can do those calculations. This is the key figure, I suppose, for Tacoma Narrows, if you look at it. And you start off, this is for the drag coefficients you'd expect to see for a cylinder versus for a sphere. So a two-dimensional geometry versus a three-dimensional geometry. And I guess they chart the behavior here for a cylinder in terms of these little figures here, which I can't get both on at the same time. And if you look at the initial portion here, this is this 24 over Reynolds number, which is the one for Stokes flow for a sphere. Slightly different, I guess, this gradient for a cylinder. But you see, as you start off at this point here, the flow hugs the cylinder, and there's no separation. As you increase the Reynolds number, then you begin to get separation at these eddies behind it. But if you look at a snapshot, it will always look the same. If you look at this point, this is the Tacoma Narrows, where the velocities are high enough that you start shedding off alternately an eddy from the top and then an eddy from the bottom, and then these get carried downstream in the wake. And of course this separation, boom, 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 from the top and the bottom are what gives this force to the bridge, which starts oscillating. And if it happens that the frequency at which these are shed happens to be the same as the characteristic frequency of the bridge, then you get it set into resonance and it pulls itself apart. And as you keep on increasing the velocity, you get into these regimes where the wake now comes off at basically mid-waist height and has this kind of chaotic wake in the back without this von Karman vortex street, which is here. And as you keep on increasing the Reynolds number, increasing the flow rate, then this separation, instead of being at 90 degrees, if you like, around here, comes at some number which is something like 125 degrees. And then as you keep on, and this has actually the lowest drag. And so this is kind of curious, because as you get more turbulent flow, rather than having more drag as you'd think, it has less drag. The drag coefficient's reduced. Of course, the velocity is increased, and so the drag force, which is proportional to what is it? CD a half rho V squared A. A stays the same, density stays the same, coefficient of drag has reduced, actually almost by an order of magnitude here, right? By 10 times if you look on this. This is a log chart. But of course, the velocity is also increased. So if you've increased the velocity 10 times here, then you've increased the velocity squared 100 times. And so the drag force is increased, but it's in response to a coefficient of drag which is decreasing. And so it's just, this is the scaling value. And so this is the reason why you want golf balls to be dimpled, of course, is that, as we'll see a little later, that this transition to this low magnitude of drag is controlled by the surface roughness, just as it was in pipes in the Moody diagram, that we had a whole series of different magnitudes of friction factor. These were for values of roughness which are quite rough, and these were for values of roughness which were quite smooth. And so the transition to turbulent behavior was a function of the relative roughness. Maybe too much that we need to talk about here. But the point is that you have to be, to address your question, you have to be working in the right regime. The flow regime has to be the correct one. So we went through the two examples, so I won't go through these again. If you want to look at them blow by blow, they're included in the videos that are online, because I think we went through them in great detail. So one for a sphere dropping through liquid. The second one for what is the velocity you have to loft a particle of ice, a hailstone, as it drops through a cloud. Of course, that's the mechanism by which hailstones get formed. They get recirculated multiple times in a cloud and get coated with extra layers of ice as they go into the cold regions of the cloud until they're large enough to drop out against the up currents. One of the videos we had was about the A380 and taking it up to Mach 1. And the reason that's important is because coefficients of drag, the forces that are applied on structures, change quite markedly as you get to the speed of sound. So Mach number is just the ratio of the speed you're going at to the speed of the acoustic wave speed in that fluid. In air, it's the velocity that you hear me speaking to you at, which is something like 700 miles an hour. And so the reason that you're interested in what happens to a structure as you get close to the speed of sound is that the forces on the structure really build quite drastically as you get close to it. And the reason for that is that you have this so-called Mach cone, and you can imagine that the way in which you dissipate forces from a structure is by sending them away at the speed of sound. If the structure that you're traveling on is moving at the speed of sound, and that stuff is trying to get away from you at the speed of sound, it can't get away. And so basically it traps all the energy that you're pushing through the air at in the area around the structure, and it applies very big loads to the structure. And so you can imagine that it's like a ripple on a pond. You drop a stone into a pond, the ripples go out at some velocity, the celerity wave speed. In air it's the speed of sound. And if it can't, it goes this amount of distance in this given time. When the plane is here, between the plane being here and the current time, it's gone this far. When the plane is here and the current time, it's only gone this far. And so you get this cone that traps in basically all the energy that you're trying to push through the atmosphere, and you put very large loads on the flight structure. And so most airliners go at 500 miles an hour versus 700, so probably 70% the speed of sound, because you don't have to build them to sustain the higher stresses, unless Concorde, which doesn't fly anymore, right, which went 2 times the speed of sound, 1400 miles an hour. Except it's too expensive to run, because you have to apply, and again, right, so to go twice the velocity, so if a normal airliner is going at 70% speed of sound, Concorde goes 2 times the speed of sound. So to go 3 times faster, you have to provide 9 times the force, right, from the square relationship. And so if you have 9 times the work that you're doing, then you have to provide 9 times the energy to get there. And so it's expensive. This is a blow up of this little region that we showed here. This region here. And this makes the point that I was making to you earlier, and that is that as you go, if you look at relative roughnesses, that particular diagram was either for a smooth sphere or for a smooth cylinder, but this is for a sphere that has certain roughnesses. So the roughness is quite large here, smaller here, and smooth here. And you see what happens is that you get this regime occurring progressively earlier, the rougher it gets. And so one of the reasons that you put dimples on a golf ball is that you want to get to this low drag regime faster, so the ball can go through the air more efficiently if you give it a whack with a given force. And so the reason that golf balls are dimpled, of course, is exactly that you get this to this low drag coefficient regime at a lower Reynolds number than you would if it was smooth, and therefore it can go further. So, but curious as to whether someone does that for their presentation. What else? Boats. Of course, a wake, the bow wave rather, and then the wake behind a ship. But the bow wave around a ship is analogous to the Mach cone around a plane, right? The wave is dissipating the energy of pushing the boat through the water. And so you have to fight against that because you're trying to get over it. And so you have to physically push the boat faster to kind of ride up onto that bow wave, that dynamic wave. If you can reduce the size of that wave by having this bulbous nose at the front of the ship, then you actually reduce the resistance. And so classical bidarkers, native First Nation kayaks of Inuit, have this thing underneath the waterline which functionally reduces the size of the bow wave and makes it more efficient in being able to push through water. If you can calculate the drag forces as we've done it for flows on particles, then you can also do more mundane things like calculate the forces on structures. And you can imagine that in this case, if you're interested in being able to design this water tower to survive some kind of force and moment at its base, you could quite easily do that if you could calculate what the drag force which is applied onto the sphere and the drag force which is applied onto the cylinder, and you could calculate the lengths over which those acted, and calculate the moment as merely the drag force on the sphere, the length over which it acts, which would be, bless you, and this would be the length of the cylinder. And so we can easily calculate these as long as we know what the velocity of the air is and what the characteristics are of the fluid that's going past it, air presumably, and we can calculate what those moments would be. So again, straightforward calculations, given that we know what the magnitude of this coefficient of drag would be. And typically we assume that this would be the drag force for a sphere. Obviously it's got something that affects the flow around it, but maybe we take those effects to be small. And so you calculate the drag for a sphere that doesn't have any impeded flow below it, and you calculate the drag for a cylinder that doesn't have any impeded flow above it due to the fact that there's ground here and a sphere above it, and we add them together to calculate the composite magnitude of drag. So again, straightforward. If you want to do it for a car, you can take the drag forces that are applied by all the different shapes of the hood and the superstructure and flow underneath it, add them all together in some way to be able to come up with the magnitudes of the composite drag that would come from the system. And I think this is kind of an interesting figure here, which looks at the coefficient of drag changing from the 1920s, Al Capone car, to the 1980s and to the 2000s, no doubt. If you look at, I was driving to work here next to a Tesla, where you look at the handles on the doors. There are no handles on the doors. There's a little silver chrome thing that you push in to do it, but it's absolutely flush with the doors. And so the design innovations, I guess, to be able to reduce drag. And so if you reduce the drag coefficient from 0.8 to 0.35, clearly you've reduced it by more than a half. Tables for different shapes you can imagine for things like flags and for parachutes to be able to calculate what the drags are. I guess the only important things to realize are that these are all functions of a given Reynolds number, unless they're for the turbulent regime, in which case, because the curves for drag versus Reynolds number typically look like this, if they're in this regime here, then so long as you're this side of the threshold Reynolds number, the Reynolds number doesn't matter. And the appropriate area. You can imagine that if you have a plate, if the plate is horizontal and the flow is horizontal as well, then the appropriate area to use for drag, if it's pressure drag, is probably going to be the frontal area of that plate, not its planiform area, but the frontal area, because that's what the pressure drag is pushing against. And so you have to make sure that when you choose the area that's used in the coefficient of drag equation, this area here is appropriate to the magnitude of the problem that you're dealing with. And the final thing that we look at, which I think is kind of a cool thing as well, I'm sure someone will do their presentation on this also. Why does a baseball spin or curve when you spin it? The so-called Magnus Effect, and that relates to what we understand about lift also. And so one way of looking at a spinning object is that if you take flow around a sphere, it's symmetric, so by definition the force above it and the force pulling down on it have to be equal, so there's no net force. But if you spin it with some rate, then what you do is you physically alter the flow field around it. And so if the flow field around it is altered so that the path of one of the components above it versus the path below it is smaller, and if you go back to our old definition, which we dispelled the other day, of the reasons for Bernoulli lift being the velocities top and bottom being different, the velocity presumably on the top, because it's being aided by this, is faster as it goes around here. So if it's going faster, velocity is larger, so there should be some net lift. And so as a result of this being spun in this way, then relative to this airflow, it should have a lift, and so as it moves, you'd expect that it would lift. So in this particular case, if you have a ball which is being spun in this direction, and you're throwing it in this direction, then the airflow is going in the opposite direction, just like this. And so in this case, the lift would be up. So in other words, if you think of throwing it so it's got backspin on it, then in this particular case, it will go upwards if it's going this way. If you give it frontal spin, it'll do the exact opposite, because this will be pushed upside down. So the separation now would be here, around here, and here, around here. Be pulled in this direction. It'll go in this way. If it goes... And so the reasons for that are that you change the flow patterns around this and you give it basically lift. Seems strange that a sphere moving through the air would have lift attached to it, but the reason it has lift is because no longer the flow patterns are symmetric about this median line. So I think that's kind of cool. I drew it this way. This is the exact explanation here, but it's in the opposite direction. But this is relative to this flow. The ball travels this direction, the flow is going the opposite direction around it. And you can calculate what that lift is as a function of the frequency at which it spins. And then there's an example here, which I think is a cool example to figure out exactly how much spin you have to give to something to stop it dropping with rate. Might be a good one. I thought that would be kind of a cool question to ask.